Some 4.5 billion years ago, our solar system was born out of a flat rotating disk of cosmic dust and gas. A gigantic ball of hydrogen and helium formed in the center. At the disk's edge, matter came together into the protoplanets. Eventually, the young sun flared into nuclear fire, and its radiation drove leftover dust and gas into space, beyond the limits of our solar system. The sun's gravitational force helped to transform the shapeless gas and dust cloud into the protoplanets. Planetary debris captured by the sun continually bombarded the infant planets, washing their surfaces with seething magma. When the cosmic artillery finally ceased, the inner planets cooled and assumed their final shape. Not all matter succeeded in forming planets. Jupiter's strong gravitational pull captured millions of planetary ne'er-do-wells in the asteroid belt. Scientists have named 5,000 minor planets orbiting the sun between Jupiter and Mars. Ceres, the largest, is 600 miles in diameter. Still other debris evaded Jupiter's gravity and exists in orbits that cross Earth's path. One such near-Earth meteorite struck ground in Alsace some 500 years ago. In 90 at midday, there was this terrible thunderous chime. The stone fell at 300 weights here in this field of Ensisheim. Sebastian Brandt's pronouncement in 1492 made the thunderstone of Ensisheim popular throughout the German-speaking world. Until about 1980, the thunderstone was heralded as the oldest observed meteorite fall in the world. Today, its reign is limited to Europe, but it is still Ensisheim's main attraction. The stone is displayed at the town hall, cared for by the guardians of the Ensisheim meteorite. The meteorite is the guild's symbol of brotherhood, having bestowed an historic importance upon the town. Maurice Costa, guardian of the Ensisheim meteorite.
Am 7. November 1492.
On November 14th, 1492, there was this enormous bang here at Ensisheim, which could be heard as far as Basel, Lucerne, Uri, and other places. Shortly afterwards, a stone fell from the sky which weighed 260 pounds. Two humanists from Basel and a young shepherd witnessed the experience. One of the so-called humanists from Basel was Sebastian Brandt, who wrote an essay on the thunderstone of Ensisheim that same year. He interpreted the stone to be a sign from God, instructing Emperor Maximilian I to proceed in his campaign against the French. Brandt's essay was an overnight bestseller. Maximilian wasted no time in visiting the heavenly stone, from which he had 2 pieces lopped off. With his pieces reserved, he ordered the local church to protect the main body from thieves and vandals. Maximilian's orders went largely unheeded, for today, the thunderstone of Ensisheim weighs a trim 121 pounds, less than half its original weight. Emperor Maximilian wasn't the only collector. Even the German poet and philosopher Goethe owned 2 of the meteorite's fragments. Around the time Ensisheim received its meteoritic messenger, cosmic material was being put to use elsewhere in Germany. Unaware of its origin, builders mined stone from this quarry to erect one of Germany's most dazzling late Gothic churches, St. George's Church at Nördlinger. The stone consists of impact glass and shocked rock fragments formed by a meteorite strike in this very area 15 million years ago. St. George's Church is indeed a heavenly building. Sebastian Brandt's divine interpretation at Ensisheim characterized scholarly opinion in the Middle Ages. By the Enlightenment, scientists shunned this belief in miracles and relegated meteorites to the world of absurdities. In 1794, physicist Ernst Chladni advanced the idea that meteorites consist of extraterrestrial material. His colleagues ridiculed him for his revelations, scoffing that he must have suffered a blow from such a stone. But his theory was confirmed by an enormous meteorite bombardment in France in 1803, an event undeniable by his once critical colleagues. It was not until the mid-19th century that Chladni's students could transfer meteorite research from the realm of magic to science. At the time of his death in 1832, he'd seen meteorites become invaluable objects of research, providing the only access to the chemistry of extraterrestrial objects. Starting with 2 pieces of the Ensisheim thunderstone, Chladni had become the father of scientific meteorite research. As witnesses to the birth of our solar system, meteorites are some of the most important research tools of planetary science. The world's largest meteorite research centers expend enormous resources in order to trace the history of the fallen messengers. Researchers at Philadelphia's University of Pennsylvania examine meteorite fragments for cosmic clues. With a $1 million tandem accelerator with incredible sensitivity and precision, they measure the amounts of very rare isotopes produced by cosmic radiation in space. University of Pennsylvania physicist Jeffrey Klein searches for rare isotopes within meteorite fragments in order to undertake a journey back through time to the origins of our solar system.
From cosmogenic radionuclides, we learn 3 things. We learn about the fragmentation history of meteorites, which tells us where they came from and how they arrived on the Earth. We learn about how long the meteorites have been sitting on the Earth by decay of these radioactive nuclides as they lie in Antarctica or some other place. And finally, we can turn the picture around and learn something about cosmic rays which produce these radioactive particles, their constancy and their variation, and even where these meteorites were bombarded in space.
Viennese geochemist Christian Kurbel also studies the trace element contents in meteorites.
Aus diesen Untersuchungen lernen wir, zu welcher Zeit und unter welchen
The trace elements allow us to determine the pressure and temperature conditions at which these meteorites condensed in the solar nebula. Further, they tell us about the temperature that existed during the early history of the parent bodies of the meteorites. Meteorite research has a long tradition in Vienna. Its Museum of Natural History houses one of the largest collections of meteorite samples in the world. The foundation of the museum's collection was laid in the early years of the 19th century. In 1806, Carl von Schreibers took over and extended the initial collection, then consisting of only 7 heavenly stones. He gave his name to Schreibersite, a mineral found only in meteorites. By 1820, the museum's collection had grown to almost 40 meteorites, a distinguishing size for any museum at that time. Schreiber's successors followed his lead and maintained Vienna's tradition as an important collection site for these heavenly stones. But then the turbulences of both world wars brought collecting activities to a halt. Only in recent years have additions been made to the collection. Vienna's Museum of Natural History now owns more than 5,000 pieces of about 1,000 distinct meteorites. This piece of the Indonesian Prambanan iron meteorite clearly bears the scars of a sledgehammer. The original meteorite takes its name from the Prambanan temple complex in Java, where it fell centuries ago. Built in the 9th century, the Prambanan temple is located 50 miles from another Javanese landmark, the world-famous Buddhist temple, Borobudur. Stone towers overlook the spectacular terraced landscape of burial foundations. There are cherished fragments of this famous meteorite in museum collections all over the world, including Washington, Chicago, London, Paris, Berlin, and Budapest. The Western world's first fragment turned up in the mid-19th century in Holland. For centuries, the Prambanan meteorite was revered by the Javanese as heavenly iron. Since the end of the 18th century, it was preserved here at the palace of the Sultan of Solo in the district of Surakarta. Palace craftsmen forged royal daggers from the Prambanan meteorite. The traditional wavy-bladed swords, or kreis as they are called, are said to cure disease, protect their owners, and even fly through the air. It is the meteoritic kreis that is believed to wield the most mystical power. Although small fragments of the Prambanan meteorite can be found in collections all over the world, the bulk of the stone remains in this small pavilion behind the Sultan's palace in Surakarta. The meteorite's surface is badly weathered. No traces of forging are visible. The small fragment from the Viennese collection, cut from the same stone, also shows no evidence of forging. The high nickel content of meteoritic iron makes it ideal for the art of forging. When court smiths began a new kreis for the Sultan, the entire block was put into the fire, heated to the point of softness, and then the required amount was chiseled off. Meteoritic iron was used only for the pamor, the pattern embellishing the dagger's blade. The ritual weapon is also an indispensable part of young girls' traditional temple dances. Even in Java, a crease made of meteoritic iron is a rarity. In 1907, Vienna's Museum of Natural History succeeded in acquiring 5 of these daggers, a present from the Sultan of Solo to Austria's Franz Joseph I. These magnificent daggers' knobs are finely carved. Made of ivory, gold, and studded with jewels. The traditional Indonesian daggers are recognized as a sign of authority for the royal family. In Java, where belief in the crease's mystical powers is strongest, men still include the daggers in ceremonial attire. Javanese culture is not alone in ascribing mythological consequence to meteorites. One may also lie at the center of Islam. Mecca's great mosque houses the Kaaba stone, which Muslims believe was sent to earth by Allah. Copenhagen is the site of another important meteorite collection. Gavik 1, a 3.5-ton iron meteorite, was for 50 years the most important exhibit of Copenhagen's Geological Museum. In 1963, an even larger specimen was added to the collection. Agpalilik, weighing in at 20 tons, is exhibited in the museum's courtyard. These 2 iron stones have much in common. They are both remnants of the same 200-ton meteorite which broke up in the atmosphere and landed in Greenland some 3,000 years ago. Discovered in Melville Bay on Greenland's northwest coast, these meteorites are part of what's known as the Cape York Group. Eskimos extracted iron for their harpoons from iron meteorites. Captain John Ross, while looking for a Northwest Passage, acquired tools made of meteoritic iron from the Inuits as early as 1818. Polar explorer Robert Peary laid claim to the largest of the Cape York meteorites at the end of the last century and transported it to New York. Peary extracted the world's second largest meteorite from its icy tomb for New York's American Museum of Natural History. It is called Anigito, the tent.
But it wasn't until 1894 that Robert Peary, the great explorer, who later on went on to be the first person to the North Pole, was shown where this meteorite was. And then it took him 4 years to bring this huge, magnificent meteorite back to New York, where it has been for a long time. Now, this is an iron meteorite, and it weighs 34 tons. When Peary first saw it on Meteorite Island, it was mostly buried in permafrost, so it was very difficult to get out. He went back a second summer and tried again to get it out, but realized he still couldn't move this thing. Came back a third summer with a larger ship and larger hydraulic jacks, and they basically got the meteorite out, lifted it up, and had a series of cables where they were moving it down the slope. one thing they didn't realize until the meteorite was on the ship was they wouldn't have the use of a compass, because the compass was pointing to the meteorite. And so they started out, and they did it by dead reckoning. And the first month, the seas were very rough. The second month, they were less rough. And finally, they got it to New York in October of 1898.
The meteorite spent several years in Brooklyn's port before making its home at the museum.
And then by 1907, it was bought for the museum, and then it was hauled up the river, and with a team of horses and wagons, it was brought to the 77th Street side of the museum, and it has been there since 1907.
Greenland's Cape York Group meteorites rank among the world's most important because of their number and weight. "20 fragments have been found with a combined weight of 58 tons. Not all of the Arctic's meteorite treasures have been discovered. There are probably many more. Nevertheless, the richest source of meteorites to date lies at the opposite end of the world, in Antarctica. In 1969, a Japanese glacier explorer literally tripped over several meteorites. He accidentally discovered that the icy continent is much more than just a frozen kingdom of glaciers and wild animals. Subsequent expeditions proved the Antarctic to be the world's most important meteorite depository. International teams have systematically searched the Antarctic ice fields for meteorites. In 1970, only 2,300 meteorites were known on Earth. Since the discovery of the Antarctic's deposit, that number has nearly doubled. Scientists have identified more than 10,000 single pieces from between 2,000 to 4,000 meteorites. Much to the delight of scientists, the so-called blue ice fields provide out-of-space messengers by the dozen. What produced the Antarctic stockpile? Meteorites fall on the surface of glaciers and in time are packed into the ice. Over thousands of years, the glacier acts as a huge conveyor belt, transporting the meteorites up against any barrier it cannot cross. The strong Antarctic winds then gradually remove the snow and ice, exposing the wealth of meteorites. Thus, the Antarctic has become the cosmologist's meteorite treasury. American Antarctic expeditions deliver meteorites to NASA's Johnson Space Center in Houston, Texas. Antarctic meteorites are truly ancient messengers from space. Nearly all of them were packed in ice for hundreds of thousands of years. Most meteorites discovered elsewhere are only several hundred years old. Evidence of any earlier impacts has not yet been found. To preserve their first-hand testimony on the origin of the solar system, these Antarctic meteorites are kept under special conditions.
The meteorites come back from the Antarctic and frozen, and we store them in the freezer here until we're ready to take them out individually and put them into our nitrogen cabinets for drying and bringing them to room temperature.
Once the meteorites are examined and classified, they are made available to international scientists for inspection. The age and large number of Antarctic meteorites furnish clues as to the meteorite concentration in the solar system. Many unknown, or at least little known, kinds of meteorites have been found among these ice-packed fragments. Some have even caused a meteoritic sensation. This is, in all probability, a meteorite from the planet Mars. Mars is our next outer neighbor in space. The pockmarked red planet is only half the diameter of Earth. In the 1970s, the Viking missions detected specific gases in Mars' atmosphere. Some meteorites have been found to contain the same mixture of gases and are thus Martian candidates. Another indication of their origin is the geologically young age of these meteorites. The Shergatti meteorite, for example, crystallized a mere 360 million years ago, indicating to geologists that its planet of origin must have been geologically active at that same time. This fails to apply to any asteroid and fits just one planet well: Mars. The surface of Mars, with its deep canyons and enormous extinct volcanoes, indicates that the red planet only recently ceased its geologic activity. Meteorites have made their mark throughout the entire solar system. Numerous meteorite craters are the prominent feature of Mercury's landscape, the planet closest to the Sun. In 1976, space probe Mariner 10 flashed to Earth these images of Mercury. Mercury's ancient surface of craters has changed little since it first came into existence. This is one of Mercury's largest craters. It probably resulted from the impact of a minor planet. A huge ring mountain surrounds the crater, and enormous clefts in the planet's crust are found within. Meteorites continue to strike Mercury, their force only slightly slowed by the planet's thin atmosphere. Craters have also been detected on Venus, but on the third planet, Earth, where the atmosphere burns up most smaller bodies, erosion and volcanism have drastically reduced most of the signs the messengers have left behind. Mars, as we've seen, exhibits more craters. Like the other three gas planets, Jupiter's surface is not solid. But its moons are scarred by cosmic bombardment, like Ganymede, the largest moon of the solar system. Io abounds in active volcanoes. 16 moons of Jupiter have been discovered. It is likely that some of Jupiter's outer satellites are minor planets attracted from the asteroid belt and trapped by the gas giant's enormous force of gravity. The 21 known moons of Saturn are also scarred by numerous craters. Its famous rings, on the other hand, consist of ice and rock fragments, perhaps matter that never united into moons, or possibly the remnants of former moons that crashed into one another. Uranus boasts 15 moons. Its 5 largest satellites also show signs of numerous meteorite impacts. In 1986, the spacecraft Voyager 2 passed the solar system's other ringed planet and allowed us to take a closer look. Uranus's axis of rotation is tilted by more than 90 degrees, suggesting that soon after it formed, the planet was struck by a huge object. Neptune also has its moons, like some of Jupiter's satellites, presumably trapped asteroids or even cometary nuclei. The surface of Triton, its largest moon, is marked not only by heavy meteorite craters, but also by active ice volcanoes. Triton is the solar system's only moon whose direction of rotation is the reverse of the planet it circles. But let's return to the world we know best, our blue planet Earth, and to a nearby celestial body heavily marked by cosmic bombardment, our moon.
Charlie, I don't know how the big man must see things, but if his view is any better than ours, it's got to be fantastic.
On a clear night, meteorite craters on its surface can be seen clearly with a simple telescope or binoculars. When meteorites strike the moon, lunar fragments are ejected. The Japanese Polar Research Institute houses one such lunar fragment. Japanese scientist Keizo Yanai. This is one of the world's most valuable meteorites. Our research has proved that it comes from the moon, in fact, from one of the lunar seas. Initially, we didn't know where this messenger from space had come from, but now we are sure. It is a lunar meteorite. After 17 Apollo missions, the moon has become a familiar world to us. Astronauts have stood on the moon's surface 6 times, collecting rock samples and enjoying the lessened gravity.
I believe it, Charlie.
It's raining, John. Look at it go, would you, Charlie? You got all your steering. It's straight. Oh, this is going to be some kind of different ride.
Hippity hoppity, hippity hoppity, hippity hopping over hill and dale. Hippity hoppity, hippity hoppity, hippity hopping over hill and dale.
Yet the lunar samples revealed only limited information on the birth of the moon. Eventually, it was lunar meteorites from the Antarctic which confirmed the theory now thought most plausible. Billions of years ago, a Mars-sized asteroid collided with a young Earth. Some of its mass vaporized on impact. Some of it was absorbed by the larger Earth. Yet another part was ejected back into space, accompanied by terrestrial matter, and was held in orbit around Earth. The chemistry of the moon appears to confirm this theory. Compared to terrestrial rocks, lunar rocks are poor in volatile elements, elements that would have vaporized upon impact. Many aspects of the origin of the moon are still open to question. Perhaps these will be answered someday soon by continued research of lunar meteorites by Japanese scientists. There is another remarkable meteorite from the land of the rising sun. A milestone in the history of meteorite research is preserved on Kyushu, Japan's most southern island. Kyushu is the center of Shintoism, Japan's traditional religion. Shinto translates to God's path. The worship of nature and ancestors are its prominent features. Unlike Buddhism, which is equally common here, Shintoism embraces the worship of numerous gods. The sun goddess, Amaterasu, rules the sky. The moon god, Tsukiyomi, is the master of the night. The gods are worshipped in small temples called miya, or noble house. Suga Jinja, a Shinto shrine close to Nogata, houses a very special treasure, the oldest meteorite whose fall was ever observed. The sky was brightly illuminated when a terrible explosion intruded on the quiet of the Shinto shrine. So begins the legend recorded more than 1,000 years ago. In 861, the meteorite reportedly pierced the shrine's roof and embedded itself in the temple's floor. The legend of the flying stone spread throughout the country. But over time, the fist-sized meteorite was forgotten outside the temple walls. The meteorite resurfaced 1,000 years later. In 1979, a Shinto priest, Masaharu Iwakuma, allowed the priceless piece to be examined by scientists. Their research confirmed the stone meteorite's place in history. The 18-ounce fragment is the world's oldest observed meteorite fall. This is the Nogata meteorite. The lid of this box tells us when it fell from the sky. It was on April 7th, in the 3rd year of Jogan. According to the Western calendar, on May 19th, 861 AD. The location of its impact is within this shrine, and there is a story that people from the village came to dig it up. As heaven sent it to a holy place, the meteorite became our shrine's treasure and has been preserved as such for all these years. At night, a bright flash of lightning was followed by rolling thunder. This is the traditional story of the Nogata meteorite. In 1980, the Nogata meteorite edged out the thunderstone of Ensisheim as the world's oldest observed meteorite fall. A few years later, in 1984, the United States sent a space shuttle on a meteorite mission into space.
2, 1, fire!
During that mission, NASA astronauts launched the Long-Duration Exposure Satellite, LDEF, into orbit to investigate, among other things, micrometeorites, or minute particles of cosmic dust. For 6 years, the satellite was exposed to the stream of these particles. The Space Shuttle Columbia retrieved LDEF in January 1990. Scientists at Washington University in St. Louis, Missouri, analyzed the chemistry of these tiny meteorites. Of particular interest were the minute meteorite craters of less than 1 millimeter in diameter, and the dust particles that caused these craters. Some meteoritic particles contained microdiamonds and tiny silicon carbide crystals, pre-solar particles dating back to a time before our solar system was born. Scientist Ernst Zinner. We know that single dust particles survived this procedure and can thus give evidence on the formation of elements in various stars. By studying the dust particles, we can consequently study the formation of elements in stars and thus get information on our own history. After all, man consists of all the elements having been created by those stars, which means that it's a way of taking the history of our solar system and our own history one step further. The meteoritic dust is an important bequest from our messengers from space. It confirms that all chemical elements, even life's molecules, have their origin in the death of stars. Bolder projects are in the works, including manned and unmanned excursions to asteroids, which may someday act as stepping stones for flights to Mars and beyond. Almost certainly, those messengers from outer space can expect visitors from Earth someday soon.